All right. Prop 24 says, if two triangles have the two sides equal to two sides respectively, but have the one of the angles contained by the equal straight lines greater than the other, they will also have the base greater than the base. So it's kind of a strangely worded, and I know it might seem like I miswrote this, but I checked like 3 or 4 times. It's written really weirdly, but this is how it's written in the Heath translation as well. So, and what it's saying is fairly intuitive. It's really not hard to understand at all. So basically, the idea is, and you can see it pretty readily in the diagram, that we have these two triangles, ABC and DEF, where AB is equal to DE, AC is equal to DF, and the angle BAC is larger than the angle EDF. That's the setup, that's the hypothesis. What's the conclusion? The conclusion is that the opposite side, BC, the side that's opposite the larger angle, will be larger. So the conclusion is that BC is larger than EF, and that's what we need to prove. And this is kind of an interesting one, in my opinion, because Prop 18 and Prop 19, those were the ones that said that the greater side is subtended by the greater angle, and vice versa. There, it's a bidirectional. So that's what Prop 18 and 19 establish, and it feels a little bit like those should also establish the same thing for this. But the reason they don't, it's sort of subtle, but the reason that they don't is because Prop 18 and 19 is talking about in one triangle. So it's like saying, all right, take two sides of one triangle. The larger of those sides is going to be opposite the larger angle. Here we're kind of taking that same thing, but we're kind of like expanding it to two different triangles, where it's like, okay, well, if you have this setup, then the triangle with the larger angle will have a larger base. That's all that it's saying. Right. And just a word of, I guess, caution if you're trying to do this on your own and kind of make these diagrams on your own. This is like actually my second or third time trying to record this, because the first couple times my diagrams came out a little bit funky. This is just a side note. It's got nothing to do with the math. It's just if you want to make this on your own, these diagrams on your own, make sure that these angles really are quite different. I ran into an issue the first time when I was kind of running through this, because here you can see this is where I started. It's the exact same thing, and here's how far I made it in the proof before I realized things were going to go astray, because we're going to end up basically making a second triangle. It might not make a lot of sense right now, but if the angles are too close, so the original angles were like, here's ABC, so angle BAC is up here, and then the second triangle would have been this smaller one. What we do is we basically recreate ABC on top of DEF, but if the angle is not large enough, then you kind of end up in a situation where the bottom of the new triangle it's too close to the bottom of the old triangle. Anyways, I'll stop talking about it now because it's really not important to anything unless you're trying to make these diagrams on your own. Right, okay, so let's jump into it. I've talked enough. And this is just a proof. So this one isn't a construction, so we'll just jump straight into the proof. And I'll write out too, just because the hypothesis is a little bit strange, I'll rewrite it out. Normally I haven't been doing that, but here it is a little bit weird. So we're given that AB is equal to DE. We're given that AC is equal to DF. And we're also given that angle BAC is larger. It's greater than angle EDF. So that's what we want. That's what we're given, what we want to prove, which I won't write here. We just want to prove that BC is greater than EF. That's the conclusion. All right. So how do we do it? Well, because these are different angles, since BAC and EDF are different, and in particular since BAC is larger than EDF, the first step is that we're going to recreate angle BAC coming off of ED. So I need to just make a little line coming off over here that is equal to angle BAC. And we can do that from Prop 23. Prop 23 gives us that. So let's see here. I'll try to do this somewhat quickly without taking up so much time. So what I'll do is I'll make a circle of radius, or I'll just make maybe a line. Radius AC centered at D. And again, I know this is faint. I'm just doing it as kind of like a, you can barely see it on the video, a cue for me. It's not actually part of the proposition. So that's the first thing that I'll do. And then the second thing that I'll do is I'll make another sort of arc that has a radius of BC, but it's coming off of E, and find where these two arcs intercept. And joining, where'd my pencil go? Joining these together, joining D with this, the intersection of these arcs, will give me the angle that I'm looking for. So again, this is just Prop 23, the last prop. And I'm going to go straight there, because I know that that's also, not only is that the angle that I want, that's also the length of that side that I want. So how shall I say? I'll say construct. Maybe I'll say on DE from D, construct angle EDG is what we'll call it. EDG equal to, maybe this is not super clear, but we're creating it equal to angle BAC. And then I'll also say kind of the next piece such that DG equals AC. So here is G. Right, and this is, all of that pretty much comes from Prop 23, at least as far as making the angle goes. As far as making DG equal to AC, that's, what was it, Prop 3 maybe? Again, we're at that point where it's like once we kind of get far enough away from the common notions in the earlier propositions and the postulates, we kind of just stop justifying it because it's like, you know this already, right? Okay. So what does Euclid say next? He says let DG, okay, he says let DG be made equal to either of the two straight lines AC DF. So, right, because AC and DF are the same, and that's what I just did. And he says, moreover, next, let EG and FG be joined. So just kind of joining G here, which we just made, joining G with F, trying to be sort of careful because I've, for the last few videos, been using this charcoal pencil, which has been great in terms of like clarity on the videos, but it's charcoal. If you've ever worked with charcoal, my wife is an artist. If you've ever worked with charcoal, it is very messy, so it does a lot of smudging, so I'm just trying to be careful about that. There we go. All right, I better write that step down. Join FG EG. Again, postulate 1, but hey, we're past that, right? That was kiddie stuff. That was like freshman stuff. We don't need to justify that anymore. Okie dokie. Then, since AB is equal to DE and AC is equal to DG, the two sides BAAC are equal to the two sides EDDG respectively, and the angle between them, namely angle BAC, is equal to angle EDG, which, by proposition 4, side angle side, says we have two congruent triangles. So I'll say since, and I'm just going to kind of rewrite some of the things that I already said, since AB is equal to DE, just in keeping with maybe, yeah, I'll write it the way that he does. I was thinking about writing side angle side, but I'll do the sides and then mention the angles. So AB is equal to DE, AC is equal to DG, and angle BAC is equal to angle EDG, and all of that is by construction, but because we have that, it follows that, well, he just immediately goes to saying, well, therefore the base BC is equal to EG. Yeah, maybe I'll say that too. I was thinking about saying what I just said about the congruent triangles, but I guess it is more concise to just say, all right, well, we have that BC is equal to EG. That's prop 4. All right. Okie dokie. What more do we know? Well, since df is equal to dg, so df is equal to dg, and again, that's just by construction, both of them are equal to AC. So they're equal to each other. So since df equals dg, we know that, and here's kind of what is not written. He just jumps straight to the conclusion, but the explanation is if df is equal to dg, then dfg is isosceles. And we know something, we can say something about the angles at the base of an isosceles triangle. So since df is equal to dg, it follows that the angle dfg equals dgf. So and he says dgf, I guess, first. So since, right, dgf is equal to angle dfg. And that needs some justification. That was prop 5. And then he says, in typical Euclid fashion, he just jumps straight to, well, if that's the case, he says, well, then angle DFG is greater than angle EGF. So what are we looking at? DFG is greater than angle EGF. Can you prove that? Do you know how to show that? It's not too much. Maybe if you like, take half, I'm just trying to autofocus this. Take half a second, see if you can justify, and I'll write it out here. So, angle DFG is greater than angle EGF. So yeah, if you'd like to take half a second, pause the video, see if you can prove that. I'll write it out right here, just as kind of a note. The reason is because, right, what is the reason? DFG, which is equal to DGF, is larger than EGF. Yeah, so the reason is because angle DGF, if I was to write it all out, DGF could be written as the angle DGE plus angle EGF. And DGF is equal to DFG. So here we're saying if this equality holds, DGF is then greater than EGF, and DFG is equal to DGF. So that's pretty much the logic. That's all that's going on in there. All right, and then this next one is the same idea. He says, therefore, the angle EFG is much greater than the angle EGF. So I'll write that, and it's the same thing. We might want to kind of just make another line, fill in some of the blanks that Euclid didn't feel the need to fill in of why this is true. So thus, angle EFG is much greater. I don't have a symbol for much greater. We don't have that. So EFG is much greater than angle EGF. And why is that true? Okay, EFG is greater than EGF. Well, probably because we could say that EFG is equal to EFD plus DFG, and we just said something about that. So I'll write that out. And this is because angle EFG is equal to angle EFD plus angle DFG. And so right here from this equality, we get that angle EFG is greater than angle DFG, and angle DFG is greater than angle EGF. So yeah, this sort of chain of inequalities is what gives us this, that EFG is greater than EGF. All right. Well, these are also parts of a triangle. So what does he say? He says, and since EFG is a triangle, having the angle EFG greater than the angle EGF, and the greater angle is subtended by the greater side, the side EG is also greater than EF. So maybe I'll say in triangle EFG and triangle, so EFG and greater than the angle EGF. All right, it's just in the same triangle. Jeez, EFG, EGF, that's the same triangle. I wonder, can I erase this? Will it erase? Not very well, maybe well enough. That's okay. In triangle. So we're just now we've whittled all of this down to a single triangle, and now we can use prop 19 is what's going on there. So in triangle EFG, angle EFG greater than angle EGF implies that the side that is opposite EFG will be larger or greater than the side that is opposite EGF. So EFG is opposite GE, or he says EG. So EG is greater than the side that is opposite EGF, which it might seem a little bit weird, but that's EF. So EG is greater than EF. And that comes from prop 19. That gives us that. But EG is equal to BC. We stated that somewhere, right here. BC is equal to EG. So since BC equals EG, it follows that BC is greater than EF. And that is what we needed to prove. That was what we initially set out to prove. So, yep, that's the end of the proof. QED, therefore, etc.